over 60,000 lower limb amputees in Great Britain. Over 4,000 new patients are seen by limb-fitting centres each year, and this number is increasing. This man is a bilateral amputee, and like the others you'll see in this film, is fitted with a new type of artificial leg, which is of modular construction. The leg has been developed by the artificial limb industry to give performance at least as good as those of traditional construction, to give amputees as much freedom of movement as possible, and at the same time to be assembled quickly and easily by the use of pre-manufactured standard interchangeable component parts. This facility enables a much quicker delivery of the finished limb to the amputee, with repairs easily carried out by replacement. Confidence in a prosthesis is influenced by its function and cosmetic appearance. Amputation in this case was well above the right knee. These 12 people aged between 13 and 58 are all wearing either above or below the knee modular legs. The length of time since they were first fitted varies between 1 and 3 years. Their performance can be gauged by watching them mount a ramp and steps and complete the more difficult task of going down steps. Traditional artificial legs have become sophisticated, but individual construction prevents the shortening of delivery times and the time required for repair or adjustment. An important advantage of the modular leg is that components can be held and assembled at local limb centres. As would be expected, the below-knee amputee can negotiate the obstacle more easily. The first stage in limb fitting is stump measurement. For the prosthetist, the main objective is to determine the size and shape of the socket, which is custom made for each patient's stump. The doctor would be more concerned with determining stump function and the general physical condition of the patient. Sockets vary in material and method of manufacture. Wood is often preferred in humid conditions. Blocked leather is malleable, absorbs perspiration and permits ventilation. Metal is rigid and light, but is time-consuming to make. Fiberglass cannot be adjusted, but is light, sufficiently strong and rigid. Whatever the socket, the modular leg can accommodate it. The order of assembly onto the chosen socket at the top of the display is now demonstrated. First, the 3 struts are shaped to the socket and finally secured by rivets. A metal alignment cup follows, also fitted by rivets. An alignment device is secured by a single high-tensile bolt with nut and washer. Beneath this, the selected knee mechanism is similarly attached. The thigh covering, made of plastic foam, can now be added. Next, the knee cover. A metal cradle follows, and inside this goes a pneumatic swing phase control, a mechanism which controls extension and flexion of knee movement. The anodized shin tube comes in various sizes and is matched to give the correct knee height of the patient. Special bonding and 2 fixing pins secure it to the cradle. Likewise, the ankle component. Next, the foot. Now, to complete the cosmesis, comes the foam for the shin, covered by a plastic skin, and finally the thigh skin. So now the leg is complete in size, shape, color, and texture. In practice, the assembly is carried out in 2 phases. The first phase would be followed by walking trials. For demonstration purposes, this leg has been assembled considerably out of alignment. Adjustments can be easily made. To make angular correction, the upper of two locking nuts is slackened. Further possible adjustments are shown with this marked assembly, rotation. Above the knee mechanism is the second nut, which when slackened allows anterior and posterior, medial and lateral positioning. When both nuts have been tightened, walking trials continue until performance and leg matching are optimized. This trial and error facility can be quickly completed at a day visit and avoids the usual delay for traditional limbs to be altered. This patient's gait is now correct. Adjustment to the below knee leg can be similarly carried out. Walking trials again confirm the results. Walking trials are followed by completing assembly and cosmesis. Here the thigh has been foamed in situ and is being shaped. After shaping, a plastic skin is used to complete the thigh finish. The shin foam is pre-shaped to various stock sizes and will be similarly covered. The completed leg is checked on the patient. A range of knee mechanisms are available as with traditional legs. But the advantage here is that components can be changed without constructional alterations to the leg, so that once amputees have gained confidence with a simpler unit, they can progress to one which can give them improved function and mobility. One of the alternatives that can be prescribed is an automatic knee stabilizing device. This enables weight to be applied to the leg even when the knee is bent. Once the weight is taken off, the knee can move freely. This versatility helps to meet the widely differing needs of amputees. Development of modular legs has been over 7 years, and during this time, testing and assessment has been undertaken by the Biomechanical Research and Development Unit and Scientific and Technical Branch at Roehampton. A special rig allows walking stress to be monitored and recorded. The data collected is later analyzed by a computer. This modular leg is believed to be the first in the world to have undergone such rigorous testing during development, and continuing research is going on to effect further weight reductions without sacrificing safety, and to extend the range of amputees for whom it can be prescribed. Each test run, with up to 7 variables, can be monitored. These tests are monitoring 6 individual aspects of load within the legs. Each test run produces up to 50,000 numbers that are recorded for later analysis. This elaborate equipment helps to cope with the data handling problem, and the visual display unit allows test variations to be simulated and the results tabulated in a convenient form before printout. The analyzed results are then used to set the standards of strength that will ensure the structural safety of the leg when worn by amputees. In this static destruction test, A foot socket, shin tube and cradle are compressed until breakage occurs. In this case, by 5 times the load of normal use. Such testing not only ensures the safety of the completed limb, but indicates where redesign can safely achieve weight reduction. Another type of destruction test involves a cyclic bending action. This will also continue until a fatigue fracture takes place. Apart from laboratory assessment, clinical trials were carried out for over 3 years before the leg was finally approved for general supply to National Health Service patients. But whatever the test results, the final approval must come from those who wear the leg. Are they able to lead a normal life in work and recreation? This man has amputations of both legs, one above and one below the knee. Apart from his moped, which he can ride with agility, he also drives a car. He undertakes internal decorating, including the hanging of wallpaper, which involves the use of stepladders. This girl had a below-the-knee amputation 6 years ago, then aged 7. She also enjoys cycling, swimming, hiking, using a trampoline, and cross-country running. Another below-knee amputee who undertakes an active job in a slaughterhouse. He's also worked in a butcher's shop, is a keen gardener doing his own digging, and drives a car without modification. Above-knee amputation with only a short stump. She has a full-time job, which she gets to by public transport. She enjoys dancing and has started riding again after a gap of 6 years.
When you go around the corner, for instance on this train, you don't want to use your left leg to pull out and let it go.
This man with below-knee amputation works on a fire crash tender, and in his spare time is able to enjoy boating without difficulty. He plays football with his children, swims, maintains his own house, including ladder work and roof repairs. His job involves him in walking up to 5 miles a day. He says he's in no way restricted in the type of life he wants to lead. The people we've just seen, and thousands like them, are leading a full and active life with the aid of these modular legs. In the manufacture of these legs, quality control is assured by inspection checks at all stages of manufacture and assembly. National Health patients are supplied with artificial legs through the British health departments. From developments now being undertaken, the adaptability and flexibility of the modular lower limb system will bring increasing benefits to patients of all ages and all levels of amputation.